Oh, I just got it on this, so there we go. Very good. Thank you very much, Dimitri, and it's really great to be here. So yes, today I'm going to be talking about magnetized high energy density plasma experiments. So this is going to be a very high-level talk. I'm just going to dip into a few topics in a relatively shallow way, but please, ask some questions. I'll pause after each little section so we can have a chat about stuff so that we don't forget everything by the end of the talk. As Dimitri said, this picture was taken on the MAGPIE pulse power generator at Imperial College. Each of these little cylinders here about the size of my thumb. So I don't know what perspective you need to get that. And this was just a nice long exposure image that we use for publicity and to get grant funding and things like that. So there's very little quantitative information from this, but it is rather beautiful. I have a huge acknowledgement slide, and this is mostly because of the work with Sandia National Labs. And when you start working with experiments on the Sandia, you start getting a huge number of people involved. But we also have lots of collaborators around the world. I've got 2 grad students, another 2 have just joined my group, and they've been doing great work. We've got some familiar names here and some people you might know from other universities as well. Just move this chair. And yes, we have some funding from NSF and NMSA, so thank you very much for that. So I'm going to start with a slide that I stole from Dimitri, because I think it's rather beautiful.
It was certainly very much improved.
Well, there we go. And can I just say, after I used this slide in another talk, and I've already seen versions of it show up in several other people's talks. So this is a meme now. You've created a meme that people are ripping on. So, but I think so. My take on this is that we can think about what's going on in plasmas in terms of where the energy is stored in the plasma, and also the processes that convert between those different types of energy. And I find this a very interesting way to sort of conceptualize the experiments that I do. And in particular, what I've done here is some things I am not able to access or I'm not particularly interested in at the moment. I put those in gray. So it's very hard with the experiments I do to do non-thermal particles. So I sort of ignore all of those. And then there's also things like turbulence and the magnetic dynamo, which are being well studied in laser experiments at the moment. And so I sort of back off from those and let other people deal with that at the moment. But one of the things that makes the pulse power experiments I'm going to talk to you about so interesting is that we end up naturally with a system where our magnetic, thermal, and kinetic energies, these sort of 3 principal energy components you might think about in the plasma, they're all roughly equal. And so all of these processes are actually really, really important. We're not in a system where the magnetic energy is either dominant or completely subdominant. So all of these processes strongly affect the dynamics inside the plasma.
I'm sorry, I have to ask.
Yes.
Do you mean it's hard to study non-thermal particles, or it's hard to get non-thermal particles?
So the plasmas we make are generally very collisional. Short mean free paths. So there is some tantalizing evidence for non-thermal particles and kinetic processes, but we're not really sure where that's coming from at the moment. Generally, if you calculate a mean free path, you would think this plasma is very collisional. So it's hard to say. The Dreissier field is hard to exceed, so it's hard to get like acceleration of particles to very high energies. So whereas in laser-driven experiments, which you may have heard of, that's a lot easier to get into those conditions. So, yeah. So I will go through a few of these processes in this talk today, but I just wanted to give you this sort of overall picture. There'll be quite a lot on reconnection. I have a big interest in turbulence, and I have some preliminary results from some turbulence work I did on MAGPIE, and I'll try and talk a little bit about what I like to do on PUFFIN, which is the machine that we're building at MIT. But I mentioned this idea that pulse power can be used to produce plasmas where you can see all of these processes. And so I'll talk a little bit about pulse power, and this is based off a conversation I had with Dimitri a few months ago, where he was grilling me about how pulse power actually works. So what we have effectively is a system that compresses energy in time and space. And we start out with some large capacitor bank that we charge up to high voltage, hundreds of kilovolts or 100 kilovolts or so. And maybe we dump 10 kilojoules or 100 kilojoules, a hand grenade or few hand grenades, into a volume of about a meter cubed, right? So our power density as we're charging this up is about 100 watts per meter cubed. We charge it up for a few minutes or so. And then what we have
is that just including the capacitors or also the space around them?
So the capacitors and all of the insulating dielectric oil or air or whatever else you have around it. Yeah. So this is like a Fermi estimate, right? So it's not exactly a meter cubed. This is on the order of a cube kind of thing. So maybe you have multiple capacitors. Maybe you have a Marx configuration to do voltage multiplication. All sorts of different things are possible. And then what you have is some switch, which you've kept open while you're charging this up. And the switch leads to a tapering transmission line of some type. And at the end here is your load. So the load is the thing that you're going to turn into plasma. Maybe it's made out of some thin wires or foils. And so what we're trying to do is get the energy that's stored in here into here in a very short amount of time and a short amount of space. And so we close our switch and our transmission line tapers down. Our capacitor bank discharges with a sort of RC time in about a microsecond or so. And we also taper the power down so the energy is focused into a small volume of about a centimeter cubed. So that gives you huge compression in time and in space. And so we end up with 10 to the 14 times higher power density here. And that's what we need in order to actually make a plasma.
Thank you.
I think Dimitri's actual question at the conference was, why is this hard? So this is my attempt to demonstrate why this is actually quite difficult. So, but these machines have been around for a long time. The technology is relatively mature, but there are still lots of issues associated with getting that power density there. But why do we need this much power density? Well, if you just had that much energy and you slowly pass it through some wires, they would get hot, right? But they wouldn't become a plasma. And what we need to do is we need to get the ohmic heating up so high that it absolutely dominates over the radiative cooling so that we can actually form a plasma here. And here's an example of a plasma load that I'll be talking about later on. This is what you saw in that photo on my first slide. So these are, again, about the size of the top of my thumb. This is an exploding wire array. There's a cage made out of, a cylindrical cage made out of thin wires, and it surrounds a thick central conductor. And the current will go up through all of these wires and then down through that central conductor. And as it does so, the wires are heated and they form plasma. The plasma carries a large amount of current inside it. And there's a huge magnetic field around that central cathode there of hundreds of Teslas. And that gives us a J cross B force that accelerates plasma radially outwards in every direction. And so that plasma, as it goes outwards, also drags some of the, or advects some of the driving magnetic field with it. So we have this source of supersonic, superalphanic magnetized plasma. And the plasma keeps being ablated for the microsecond or so of the drive time here. And so this is a hand-wavy argument, but you can make it a little bit more rigorous. Because you're using the same current to both heat the wires and generate the magnetic field, and that magnetic field is the J cross B force, which accelerates the plasma, you tend to end up with a system where all of the energy components are important. So this is very different from laser-driven experiments, where the magnetic energy is usually very small. And so this makes this ideal for doing magnetic reconnection experiments. And this is also the sort of equipartition that you see in many astrophysical plasmas. So it's an attractive experimental platform for astrophysical plasmas. So any questions on that before we go on to some applications? So I'll start by talking about some magnetic reconnection work that I did on MAGPIE, my PhD and postdoc. And then I will show some different paths we can take where we add significantly more current and we go up to the largest pulse power machine in the world at Z. And also what we can do if we have a much longer current pulse, which is the PUFFIN device that I'm building at MIT. And I'll also discuss a little bit some ideas I have for generating MHD, magnetized turbulence in the laboratory, and how that would be affected by going to PUFFIN. So I will go through this quickly because I suspect everyone here is quite well aware of what reconnection is. But just to sort of say where I'm coming from, we have this process where oppositely directed magnetic fields are brought together within a plasma. We get an intense sheet of electrical current that breaks the frozen-in condition of ideal MHD. And we have strongly bent magnetic field lines, which accelerate plasma flows. And we also have ohmic heating within the current sheet. So in some sense, this process converts magnetic energy into kinetic and thermal energy, but it also changes the topology of the magnetic fields. And that leads to exciting things like coronal mass ejections and other things on the surface of the sun. And as we probably all know, there was a big discrepancy between some of the early theories for reconnection, which predicted sort of 1,000 years for eruption times. And in reality, this takes place in about 10 minutes or so. And so we've known for a while that these theories from the 50s can't work, and a lot of theoretical effort has been put into trying to come up with alternative theories. And one of the ones which I'll discuss in the context of the experiments today is the tearing instability, which takes this current sheet and tears it up into small intense sheets of currents surrounded by O points in the magnetic field, which have very strongly sheared flows. And these O points are known as plasmoids, and the plasmoids are very good at effectively dissipating that magnetic energy. So it gives us much faster reconnection rates, and this seems to match some observations we have. There are other theories for why fast reconnection might take place, but I'll be talking a bit about plasmoids later, so I wanted to introduce this idea here. So how do we actually do reconnection in the laboratory? I've already introduced you to the exploding wire array as a diverging source of magnetized plasma flows. If we put two of those wire arrays side by side and we drive them in parallel, we have plasma flows which will collide at the midplane between the two exploding wire arrays, and here their magnetic fields will be opposite. And so we'll have a reconnection there that forms in the middle. And what does this actually look like in our experiment? So this is the MAGPIE generator at Imperial College. We've got a vacuum chamber here, and the lid goes on, and we pump that down to a low vacuum. The whole machine actually sits underneath here and fills a room the size of a pretty good house. And surrounding it are lots of different diagnostics. Some of the diagnostics I'll be going through today, things like Thomson scattering, Faraday rotation imaging, and laser interferometry. But that's the actual load itself. That's a photograph of it before it starts exploding. Of course, I showed you earlier a photograph of it while it was exploding. And so you blow all of this stuff up, and then you lift off the lid of the vacuum chamber, and you painstakingly reproduce it, and then you do that again and again. And we get about 1 or 2 shots a day on MAGPIE. So the main limit is actually how long it takes to pump down the vacuum chamber.
So when it explodes, what is left? I mean, the wires.
Yeah, there's actually most of it is really just the wires that go. All of the cathode pieces get a little bit bent, so you can reuse them a little bit, hammer them back into shape. These little laser cut discs, sometimes the holes get clogged and melt a little bit, but most of it's still there. And then all the carbon, in this case, these are carbon wires, just coats the inside of the vacuum chamber. There's only a few micrograms of, or hundreds of micrograms of material here, so it's not very much.
So it's like a carbon plasma?
So in this case, it's a carbon plasma, so you have to have something you can make wires out of. Carbon is about the lowest Z element we can make wires out of. You know, lithium is flammable, beryllium is very toxic, boron isn't a conductor. These are mechanical pencil refills. So this experiment cost about 50 pence, going down to the stationery shop on campus and buying up all their supply of mechanical pencil refills. So there may be purer sources of carbon. I just had one of the faculty at NSE does elemental composition analysis, and he just ran this through his device. He hasn't given me the report yet, but he tells me that there's like 5 or 6% oxygen in there. So it's not like a pure carbon plasma. It'd be nice to have pure carbon because it makes it easier to analyze it, but it's good enough. We've also done reconnection experiments with aluminum, copper, steel, tungsten wires. I'm not going to talk about those today, but effectively, as you change the wire material, you can change the amount of radiative cooling of your plasma, and that means as the plasma flows expand outwards, they cool faster, and that actually makes them more supersonic and maybe more superharmonic. So you can actually change some of the other parameters in your system just by using a radiative cooling. Okay. So just a brief overview of some of the data results from this. We are able to measure things like the electron density using laser interferometry. And so this is looking at the reconnection there from above. These little bends in the fringes here indicate the reconnection there at the center. And in fact, if you've got a good eye, you can see that there's a plasmoid there where the fringes are bending larger. And I'll talk a bit more about the plasmoids and why we think they're really plasmoids and not just density perturbations later. We also do Faraday rotation imaging from the side, so you can see the arrays here with the wires vertically, so it's the orthogonal view to this one. And here we look at the polarization of the probing laser beam, and that polarization is proportional to the line integration of the magnetic field along the probing laser and the electron density. So by combining these two sorts of measurements, we can get an estimate of what the magnetic field is as an actual image, which is rather neat. So you have a
laser beam.
So it's expanded laser beam. Yeah, it's collimated still, but it's been expanded up to, in this case, about 20 millimeters across.
Okay, so very broad.
Yes, exactly. So it's not a focused laser beam. For the Thomson scattering, we do use a focused laser beam. We pass a focused laser through the center of the plasma. Behind it is a processed electron density map. So we take the interferogram here and we do a processing routine, and this orange blob corresponds to high density.
Again, from the top of.
Yes, this one is from above. I keep switching fields of view. We do have side-on interferometry, but it's actually, and I'll show some of that later. Yes.
And this one is the same as that?
Yeah, so basically this is the same as that. I don't think it's the same interferogram, doesn't look like it.
Sure.
Yeah, but it's the same field of view. Yeah. So this is the layer here, and you can see it's sort of not completely uniform. And we fire a focused laser beam through here, and we have 2 fiber optic arrays on either side with 14 fibers in each. And so we collect the light from 14 locations along the laser beam. This is the spectra here, which is not particularly beautiful. But what you see is that compared to the initial laser line, different points are shifted by different amounts, and also the spectra is broadened. So this corresponds to velocity, but also the temperature inside the plasma. So we can get the density, the magnetic field, the velocity, and the temperature
And these
by
are
combining these diagnostics.
like functions of time. They resolve.
So they are time resolved. The laser pulse in each case is less than a nanosecond, whereas the experiment goes on for 300 or 400 nanoseconds. So effectively, it's an instantaneous snapshot. Yeah. And
Actually, you have not just a. Sorry.
I was just wondering, your polarization angle goes from -1 degree to 1 degree?
yes, it's very small.
Very small.
Very, very small. So this is a very difficult measurement, and it took us a long time to get this diagnostic working. And there are still some issues with it. So it would be nice if the angle was larger, but the only way to do that really is to have higher densities and higher magnetic fields. So
Can you change the wavelength of the?
we're already using infrared laser to get the largest wavelength shift. If we go any further, we actually run into problems with the plasma density gradients refracting the laser beam out, and so we can't make the measurement.
Okay.
So we're
So it's a
quite
real
constrained.
limitation.
Yeah.
It's, I know that in
Yeah.
astrophysics, people do this polarization sort of a thing.
Yeah.
And sometimes the polarization like goes around more than 2 pi.
Yeah.
Like Faraday optically.
Yeah.
Faraday thick versus.
So that doesn't happen here,
Okay.
just because
Really
It's a very
I mean, it's the combination of the density, the magnetic field, and the line integration. So we have a,
short.
compared to astrophysics, it's a short, low density, low magnetization, though I'm sure this is probably bigger magnetic fields and bigger density in astrophysics, but we're only integrating through 10 millimeters as opposed to 10 kiloparsecs or whatever. Some unfathomably huge number, right?
Yes.
So yes, it would be great to get this higher. I guess at least we don't have the ambiguity problem of what happens when you go around more than 2 pi.
Yes.
That sounds like a nice problem to have.
Well, and it's still measurable, right?
Yeah, it is just about measurable. Exactly. It's on the limit of what is really possible.
And what are the like circular?
Oh,
ones?
they are dust spots. No matter how hard you try, you can never get all the dust off your optics. And so these are diffraction rings caused by dust spots, which are out of the focal plane. So unfortunately, they're not beautiful like objects here. And so what we do when we get out the magnetic field profiles, we usually average over some. So this is actually very axially symmetric, uniform, right? So this system is sort of quasi two-dimensional. There's very little variation in this direction. So we do some averaging over some chunk here in order to get out the magnetic field profile.
That's great. So you have all of these indeed.
Yes, and some of these we do them in different shots, so the experiment is quite reproducible. But for example, it's difficult to run the Faraday and the Thomson on the same shot. They require a huge amount of work, both of them, to get them set up. And so to build up at different times, different measurements, we do the same shot over and over again. So my PhD thesis work, where all this comes from, we did maybe 40 shots over 3 years. So,
But nevertheless,
Yeah.
having all of these things that
so then you
resolve, because in
Yes.
in NIF, for example, I'm familiar that they have with proton radiography, right? They would
the proton radiography is time resolved on this to some extent. No? Or
well, maybe those experiments that I'm familiar with Lil Fox.
Yeah.
You kind of in a shot you can have only one snapshot.
I see what you mean. Yeah.
So you have to waste shots just
To build up.
to
Yeah.
build up.
Yeah.
the
Well, we
time.
only get one of these per shot as well on MAGPIE, but then we
No, but you have a whole movie. Oh no! So which ones are timed?
all of these are time resolved and are all once per shot. But then we redo the interferometry. Actually, we have 2 different wavelengths, so we can do 2 different shots separated by some dynamically significant time, so we can watch the plasmoids move around. And we do have a high-speed camera for optical self-emission. I'll show you later, which does take 12 pictures during
in
an
a single
experiment.
shot. Sorry
In a
for-
single shot. Yeah.
Sorry for getting stuck on
Yeah,
this, but
that's okay.
delaying you. But in a single shot, let's say Thomson scattering, you
Yeah.
have this image, right?
Yeah.
How many images do you have from a single shot?
One. There's only
Oh,
one
just
time.
one.
Yeah.
Oh.
The camera can only trigger once. The laser can only. fire
That
once.
was my question. Yeah, that's a
So
big
no, it's
problem.
this is a big limitation for all of these experiments.
Because I was
Absolutely.
hoping you have a whole movie from which.
No. This is so the theorists, they always want to have all the quantities of all the locations and all the times, and the
Yeah.
experimentalists, we can only do them like in this case, Tom scattering only along a single chord at 14 places at one
Yeah.
time. So
that's understandable.
And that's just because all of this happens so fast. that it
yes,
can't-
the camera can't trigger twice, the laser can't go twice. So the laser flash lamps charge up and discharge, and they couldn't fire again for another 10 minutes, whereas this is over in a microsecond. So big limitations to
Well,
diagnostics.
you have many of them probably. Right?
I know, and if you've got several $1 million,
Right.
I will go and do that. I'm happy to do that. But yeah, but this is it. So these things they cost a lot of money. So a Thomson scattering system is about 300K at the moment to buy the camera and the spectrometer and the laser and things like that.
And to what extent can you disentangle all of this? For example, you have to to get the density, you have to know the magnetic field.
Yeah.
Do you get them?
So for this diagnostic, we actually have an inline interferometer which measures NEDL. And so what we do for that, rather crudely, is we divide the Faraday signal by NEDL, and we get an estimate of B. So it's not actual B, it's like the line integrated, density weighted average of the components along the probing laser. So with all these caveats, we get the magnetic field. And then we know something about the symmetry of the system. It has very good axial symmetry. So this DL is actually quite easy to replace with some macroscopic length scale L. And then here we know that the magnetic fields are roughly curved, so we can have some estimate of that curvature. So they are, we can disentangle them all with a little bit of work, but there's still sort of caveats. They all depend on another measurement. But yeah, let's see.
When you do multiple shots, do the dust patterns change? Or do you like do a shot?
Yes, usually, because we try and dust the optics every time and then we disturb it. And if we didn't do that, there would just be more dust spots until it was unusable. So yeah. So pulse power labs are not good places to do laser optics because there's an awful lot of dirt everywhere and like oil, aerosolized oil everywhere. It smells really bad. Okay, I am going to keep going because I have way too many slides. Okay, so we can put all of this together. Because we can measure things like the magnetic field, the velocity, and the temperature and the density. We can estimate the amount of power flowing into the reconnection layer per unit time and the amount of power flowing out of the reconnection layer per unit time. And so you can see in the inflows, they're dominated by the magnetic energy, a little bit of kinetic energy, a little bit of thermal energy. And in the outflows, we have much faster plasma flows, which are much hotter. And conveniently, if you sum up all of these, they match up with this within error bars. So we've conserved energy. This is important as physicists. We like that. But the next question you can ask is, okay, I've conserved energy. I see where all the energy is gone. The magnetic energy is being converted into kinetic and thermal energy. But how is that actually happening? And if you calculate how long the plasma has inside the reconnection layer, where it can be heated and accelerated, it's only around for about 50 nanoseconds. And then if you calculate sort of Spitzer, Brzezinski, viscous, and resistive timescales for the heating and the heating of the ions and the electrons, they're much, much longer than this experimental time. So this doesn't really make sense. The classical heating seems to be far too slow. But of course, we have these plasmoids, and go on.
So I see that here you're able to separate electron and ion thermal energy. How did your previous measurements, were they, the last one, this?
So in Thomson scattering, you end up scattering off the ion acoustic peaks in this regime, and the separation between the ion acoustic peaks is proportional to ZTE, and the width of the ion acoustic peaks is proportional to TI. So if we stick with the Thomson scattering form factor, you can measure that. Yeah.
Is that why pure carbon would make it easier? Like the Z component?
To be fair with the Z, we have like a NLTE model that we use to decompose Z and TE into Z and TE separately. So we have like some atomic codes that helps us decompose that. But you can do this for tungsten and other things as well. The peaks tend to end up closer together. So carbon is actually, one of the nicer ones to work with.
Okay, and you end up with the same temperature for electrons and ions. So
the same thermal energy. But Z is 6 in the outflows because carbon is fully ionized. So the electrons are actually much colder, but the total thermal energy component is interestingly the same, which I don't think I have a good explanation for. We looked into something to do with the ion acoustic instability, which turns off when you meet this criteria, when ZTE equals TI. But we don't have any evidence for the ion acoustic instability.
So you're saying that, so that somehow, as you were just telling us, the classical plasma heating and collisional processes are too slow, so there is some anomalous.
There's some anomalous heating effect.
And obviously this anomalous heating does not work in the same way as regular heating would work, which would bring the same temperatures. You would have the same electron ion temperatures here. The temperatures are different, but somehow.
So why would they have the same electron ion temperatures?
In general, you have collisions.
Right. So the collisionality, the equilibration timescale is relatively long here. So we're sort of it's on the order of this 50 nanoseconds. So it's actually not unreasonable for the electrons and ions to have separate temperatures.
Okay. But nevertheless, somehow, so the temperatures are not the same, but the thermal energies are the same,
which is surprising. Yes.
Okay.
Yeah.
And is there no magnetic energy coming out?
So I will admit that's a bit of a cheat. We just set the magnetic energy to be 0 in the outflow, so we don't measure it. But I'm about to show you some magnetic probe data, and that also shows that the magnetic field is negligible. So, and in Sweet Park, you'd expect it, our Lundquist number is about 100, so you'd expect it to be smaller by some large factor. And so overall, the magnetic energy in the outflow is negligible here. Certainly, it would be within these relatively generous error bars. So, yeah. So then I now do have a movie for you. So this is our one time-resolved diagnostic. This is a very expensive camera looking at the optical self-emission. And what we've done, you can see the plasma coming in from the left and the right. You can see this reconnection layer forming. And if you spend a lot of time squinting at this, you'll agree with me that there is some sort of blob which is moving upwards, and I've marked with an arrow. We also have interferometry from this shot, so we actually know this blob is a region of higher density that looks elliptical. It looks like a plasmoid. And we've stuck a little probe in the top and in the bottom here. This probe is what we call a B-dot probe. It's a little loop of wire, and we measure the voltage across that loop, and that's proportional to the rate of change of the magnetic field. So effectively, we're measuring that magnetic field in the plasmoid. So if we look at a cartoon of a plasmoid, it's an O point in the magnetic field. So this probe should at some point pick up magnetic field pointing in one direction, negative sign, and another time it should pick up the field pointing the opposite direction with a positive sign. And in the center there should be a null in the magnetic field. So this is the raw signal from our B-dot probe. There's actually two little loops counterwound so that we can do common mode rejection. And if we take the difference of these to get the inductive signal, and then we integrate it up, we get out this magnetic field pattern here. So if you watch as the plasmoid passes over the probe, you trace out this rather nice O-point structure here.
Wait, so these are the wire cages, but what are the hotspots?
So these are the wire cages looking from above here, and this is actually the probe itself. So I don't have a photograph of it, though I'll show you some later for another experiment. But imagine a little tiny pencil of metal pointing into the plasma with a little loop at the end. So it is perturbative. But yeah.
So the probe is a hard object.
It's a solid object, and that's why plasma is shocking up on it and making that's what the surface is going. Yeah.
So what owns the asymmetry in the magnetic field amplitude?
So there's a few things. You might be able to see the signal is actually not very good. The oscilloscope was not set for the right sensitivity. And so you actually get some sort of drift when you're integrating up this signal. And so we think that this is related to some drift increasing. So I kind of implore you to focus just on the first bit. So it's really more proof of principle about the morphology of the magnetic field than maybe the best measurement of it. So this is something I want to revisit on the experiments I do at MIT. But for what we could do at the time on MAGPIE, this was pretty good.
And is each little square wave pulse one shot?
No. So this is in time. This is a single shot.
This is a single shot.
Single shot going from 160 to 300 nanoseconds into the current pulse. The current peaked around 240. This squareness here is because of the poor digitization of the signal, right? So I'm representing it as a step function. And so this is our bit depth. There's this many things. And so even the peak of our plasmoid is only 1, 2, 3, 4, 5 steps high. So this could be done much better.
And the movie on the left, is that also that same?
It's a single shot. So
shot.
it's a camera that costs about 250K, and it takes 12 pictures. But you can get up to 200 million frames per second. So it is an ultra high-speed camera. I don't think there are any other in the past.
What is it?
How does it
Optical
work?
light? No,
Yes,
what
optical self-emission. Yeah, so this is the plasma's optical self-emission, exactly. And we do this actually down the same probing line as the laser. So we have a filter to cut out the laser light, but it means you can overlay the images of the electron density directly on top of this. So I'm not showing it in this talk, but we also know what the electron density is inside these plasmoids and loops.
What do you mean self-emission?
It's just the radiation coming off it from Bremsstrahlung or line.
As opposed to like a background or something?
As opposed to like laser light or something like that we put through it. Yeah, thermal emission with water. Yeah, exactly.
Well, I remember that. Okay, so if I recall correctly, this experiment here was the first laboratory experimental demonstration of plasmoids in magnetic reconnection. Is that right?
No.
Okay.
Our paper got published 6th of January 2017. It seemed to have been delayed by a referee, and there were 2 other papers in 2016 which showed experimental demonstrations, but ours was just inside 2017. I wonder how that happened. But so there were 2 other demonstrations, one on MRX and one on T-Rex, so at Princeton and at Madison. So very different plasma regimes, because they're magnetically dominated plasmas with very low beta. And they had different ways of measuring it. In those experiments, they have a huge arrays of magnetic probes. If we had a huge array of magnetic probes, we'd have no plasma left. So we were able to use Thomson scattering and laser imaging and things like that. So our measurements were all sort of done from outside the plasma, and those measurements were all done from inside. So it's complementary work. But yeah, there have been 2 others, and there's been a few papers
Also,
claiming these in laser plasma experiments as well. And I think I'm not sure any of those have been published yet, but they're certainly on archive. So yeah,
so at least simultaneous, right?
Yeah. Yeah, exactly. So I don't know why there was a zeitgeist around that time to look for plasmoids, but it seemed to be like everyone was doing it all at the same time. So yeah. I'm going to be a bit more selective about what I talk about, I think, just to get through everything. But I will show this next bit because it sort of motivates PUFFIN slightly. So we've been looking at this in a very 2D way. And of course, a lot of the times we do look at reconnection in a very 2-dimensional way because it's easier to simulate, it's easier to think about, it's easier to do the experiments and interpret them. But one question that people have been asking is what do these plasmoids look like in 3 dimensions? So if I take my 2-dimensional plane and I just copy it down here as well, I see that I've got these O points in the magnetic field. And those O points are places where there's current concentrated. That's why there's no point in the field. And so the current has to be continuous. And so maybe we draw a line that joins one of the upper plasmoids to one of the lower plasmoids. But of course, once you've drawn something like that, that current path looks like a Z-pinch when there's no guide field. And Z-pinches are, as we know, very unstable to all sorts of MHD modes. And so one of the instabilities would be sort of a kink instability here. So the question is, how stable are these plasmoids in 3 dimensions? And people have been looking at this. This is from a few years ago now, and I think there've been more up-to-date simulations or more recent simulations as well. They start with a system in 3 dimensions with, I think it's periodic in this direction. So I think this is basically 2 plasmoids here. And then they let this simulation evolve in time, and they see that this plasmoid becomes more and more kinked. And in fact, very late in time, these plasmoids, there's many of them, they're very, very kinked. You can't really even see the plasmoids anymore. It just looks like a turbulent mess, right? So it seems like this is a transition to a turbulent reconnection. And so this is very interesting, especially in astrophysical contexts, where maybe we see reconnection spread over a broader region than we would expect from our sort of narrow reconnection layers. And so this kink instability could be a pathway for turbulent reconnection, which is another hot topic at the moment. So do we see this in our experiments? This is an interferogram or electron density map from interferometry looking from the side. So your 2 wire arrays are like this. The plasma flows are coming in. Here the magnetic field points into and out of the page. And this is the reconnection layer here, which looks very uniform. And what I've done is I plotted the centroid of this reconnection layer and then massively expanded this axis here. And you can see there's this tiny little suggestive sinusoidal wiggle on it. So this is what we were able to do on MAGPIE. And this was taken about 300 nanoseconds into the current pulse, which is after peak currents. The current is already falling. The plasma is beginning to disassemble and cool. And so this is one of the problems with MAGPIE, or limitations with MAGPIE and other pulse power experiments. At the moment, they have relatively short current pulses because they were designed to do other physics. And so this means that you can't just watch this plasma for a while and say, oh, what happens? You know, does this get more kink unstable? Do we get turbulent reconnection? Anything like that. We don't have a good idea about whether that happens. And so I will use this now to motivate building a machine at MIT, which has a much longer current pulse, so we can observe these dynamics over much longer timescales.
Yes, does this wavelength match the fastest growing mode of the kink instability?
No, we haven't done that. In fact, if anyone knows any theory of what the kink instability of a plasmoid is inside the reconnection layer, we'd love to see it, because I haven't seen it yet.
I'm
sure you know.
We asked Jeff Freiberg because he knows a bit about MHD and he wasn't sure. So, actually, so can I point out something here? So this is a line integrated measurement. So within this current sheet, there are probably some plasmoids, 2 or 3 is what we normally observe, and then lots of other plasma within the X points between it. And so I can't tell you whether this wobbliness is the entire sheet wobbling or just the plasmoids. And you can imagine you can have a plasmoid that was wobbling a lot, but because it's line integrated, it's washed out, and so you only see a certain smaller modulation. So this isn't a completely satisfactory measurement here, and I don't even know if there's a calculation that shows what the kink stability of a sweep Parker layer is, because it's not entirely clear to me that that's stable. So I think there's some open questions here. So yes, these are the 2 open questions I had, but again, I think I'm going to skip ahead a little bit. So the second one is the one I want to focus on with the machine we're building here. What other instabilities can grow on long time scales? Things like the kink. There's like Kelvin-Helmholtz instabilities that form around these plasmoids as they plow through the plasma. So I was going to briefly mention experiments on the Z machine, which Dimitri is involved in. Here we take 20 times more current and make some much larger, but still pretty tiny plasmas. And the goal there is to look at radiatively cooled magnetic reconnection. So this is a regime that's very important in lots of astrophysical systems. We're not going to be able to reach these sorts of extreme regimes in the laboratory. I'm not going to try and convince you we have pair production or inverse Compton or anything like that. But what I'm interested in with these experiments is something a little bit more fundamental, which is what does a cooling instability look like within a reconnection layer, either sweep Parker or with plasmoids, whether you have a layer which cools and then it gets compressed and then the density goes up and then it cools even more. And so this process here is a bit of a runaway kind of thing. And so Dimitri did some theory on this about a decade ago. And so we're interested in doing some experiments to look for this, but I don't have time to talk about it all. So I'm just going to show you some pictures because they're quite good fun. We've done a lot of simulation work with a MHD code that includes lots of the physics, and we simulate the whole experiment. We end up with a system that early on in time, when I let this play again.
So this is for which experiment?
This is for the experiments on the Z machine, yes. Yeah. So here we started with a system that has some plasmoids in it, and then there's a radiative collapse of the layer and it becomes extremely dense. So this is density line plotting here, dense and cold. And so we sort of have an early plasmoid phase, and then later on we have this rapid cooling phase. Yeah, I really don't think I have time to show much of this, unfortunately. Let me keep
Do you guys have time limitations?
No.
Okay, I will do this. I will skip the magnetized turbulence. Okay, thank you. I didn't want to keep people if you had other things on.
Actually, yeah, I mean, I think we all have time.
Okay, I'll slow down a little bit then.
We could just let people go.
Sure.
This is being recorded, so.
That's a good point. Yeah. So we're moving this to Z. It's the largest pulse power machine in the world. It's at Sandia National Labs in Albuquerque, New Mexico. It's a huge DOE facility. It normally does classified research in support of the stockpile stewardship mission, but they have about 10 shots per year that they allow for fundamental science. And our collaboration that Dimitri is part of, and several other people that you saw, Hantal G and Rose Fox, we were awarded 4 shots over 2 years to start with. And so it's not very many shots. You don't get much data, but you do get to play with the biggest machine in the world. And we have in the pulse power community these rough scalings for how the plasma density and magnetic energy and things like that go with current. And so the density goes about the current squared. So we expect to have 400 times more density. The magnetic energy also goes as the current squared, so about 400 times more energy to dissipate. But our cooling rate goes as density squared, the current to the 4th power, so hundreds of thousands of times stronger cooling rate. So we can really reach a regime where we have a huge amount of magnetic energy, but we can also radiatively dissipate very, very fast. And so we had to change our wire arrays a little bit. This is not exciting for people who are not experimentalists, but they are very unusual wire arrays if you're in the pulse power community.
Are they still pencil lead?
No, these are aluminum. Yeah, these are aluminum. I don't think Z would have been too embarrassed to let us use pencil leads, but they'll probably have to buy something for like, $100,000 each or something like that to justify it. Yeah, exactly. It would just be, they couldn't face themselves. They couldn't talk to their managers if they use pencil leads. So.
But maybe you could put a human figure now on this.
Oh, well,
they're
40 millimeters. They're 40 millimeters across, so they're about that big. There's 2 of them like that. I've got some photos later to with some people in, so you may be able to get the sense of scale there. But they're still tiny.
Even on the previous simulation movie that you showed on the previous slide.
Yeah,
this was very visible, right? But how many of these? So you said 150.
150 wires. So these little yellow dots here are the wires. So these take about a week, or no, I think this took about 2 weeks to build.
I remember it was very impressive. And the kind of you build them one way and then you have to turn them over, and turning this over is a major challenge, right? Maybe you can tell us about
when I get to the photos of the hardware, I'll talk through it then. Yeah, no, that's a good idea.
Can you just use an aluminum cylinder?
Also, interesting questions. If you have an aluminum cylinder, so it's continuous there, you have a Faraday cage. So there's no way for the magnetic field on the inside to get to the outside of the plasma. So when you have wires, you have a little gap, and that allows the magnetic field to push outwards and drag plasma with it. If you replace this with a continuous liner, you wouldn't get any plasma generated, and you wouldn't have any plasma flows. People have tried that.
Actually, so I'm just curious. So it's a painstaking process to have all these wires, right, individual wires. But maybe it would be easier to start with a cylinder and cut.
Yeah, so I think there are now like advanced manufacturing techniques that would be really interesting to try along those lines. Absolutely, yeah. So this is the way it's been done for like decades now, and I think Sandia will probably be the last place to try something new, because they need everything to work, right? So they have the lowest engineering risk. If you have a university machine and you've got a grad student or an undergrad who wants to go 3D print in metal, like go for it, like just try it. It'll take a morning to show whether it works or not. Whereas these shots, as you know, it takes 8 months of planning. We have to do all the planning meetings 8 months in advance, and so it's a huge amount of effort. So we can't just try something for laughs. Yeah. So in these simulations, as I was saying, there's some interesting physics already going on here that we want to look at a bit more. Color isn't so great on this screen, but take my word for it, these little red arrows are pointing at little blobs of enhanced density, which are plasmoids. I'll show that later with some other simulation data. And so there's a few plasmoids coming around. There's actually 2 of them here which are merging. The latter one is catching up with the further out one, and they're about to merge. But a few hundred nanoseconds later, then the whole layer has collapsed. It's become very narrow and very dense, and there's no sign of these plasmoids anymore. And we know that this is to do with the radiative cooling that we've put into these simulations, because we can do simulations with different radiative cooling rates. We can turn the radiative cooling off, and we can increase it as well. And so this is just like a knob that we can turn to play around with the radiative cooling. And here I'm plotting the Lundquist number here. And you can see without radiative cooling, the layer never collapses. It stays at a relatively high Lundquist number for a while. But as we increase the radiative cooling, the time at which the Lundquist number drops, because the temperature drops dramatically, gets earlier and earlier. So we think that this is actually what we're simulating is actually due to radiative cooling and not some numerical error or issue that we're having. So looking at these plasmoids, there's some interesting physics going on here. This is the electric current inside the reconnection layer. There's an incredibly exaggerated aspect ratio here, because otherwise this layer is really, really long and thin. So this is exaggerated by 10 to 1. So although these look like, squashed ellipses, they're actually really stretched ellipses still. And I plotted the electric current, but I've overplotted contours of the magnetic vector potential, so magnetic field lines. And you can see these field lines here, and there's X points between them, and O points here, and more X points. And then you've got the open Y sort of shape field lines.
So what kind of simulation? This is a simulation, right?
So the simulation, this is Gorgon simulation, which is in this case, 2D resistive MHD code with radiative cooling models and other things you need to simulate actual experiments like equation of state and stuff like that. And we're using a very simple radiative cooling model here, which is, where am I? Here. We're just using, this is basically a recombination loss model. So it's got a very simple dependence. It doesn't capture any of the atomic physics, like the line radiation. We have more advanced simulations that do capture that, but actually qualitatively, the picture is the same. And so it's much easier to look at this sort of model. We've got this multiplication factor that we use to tune the amount of radiation, and that's the knob that we have to sort of see what radiation is doing.
Basically, density and temperature is all you need to know.
Yeah, it's sort of density squared, temperature to the half, kind of thing. Yeah. So the plasmoids here seem to have a lot of current inside them. You see there's a huge amount of current flowing inside each O point, actually more than in the X points in some places, which is different from some other simulations we've seen of how the current redistributes within the reconnection layer. And because there's a lot of current flowing here, in our system, which is quite resistive, there's a lot of ohmic heating. And so the plasmoids are extremely hot. They're much, much hotter than any of the surrounding inflowing plasma or the plasma inside the X points. And because they're very hot, their resistivity is very low here. This is logarithm resistivity, and these dark points are very low resistivity. So they're also an attractive current path for the current as well. This looks a little bit like the electrothermal instability, and we've got a grad student working on how the electrothermal instability might interact with the Terring instability that Nuno and I are co-supervising. So there's some interesting theory going on here, we think. And the plasmoids are also much denser. This is a scale of density here. They're also much denser than the surrounding plasma. I don't have a great hand-wavy argument for that, but I think in some points here, the plasmoids may have already started to radiatively collapse, and so their density may already have started to increase at this point during the simulation. But the upshot of this is the plasmoids are very dense and they're very hot, so they are also very strongly radiatively cooled. In fact, if you look at the radiative loss, the power per meter cubed, the plasmoids are the only things that really light up here. So this is really interesting for our experiments because it means as a diagnostic signature, we may be able to see these little bright blobs moving around. And potentially it has some interesting implications for other systems where you are asking yourself, say in astrophysics, where is the radiation actually coming from? Is it coming from X points? Is it coming from plasmoids? If this sort of physical argument carries over to those systems, you might find that most of your radiation comes from the plasmoids, which are of course very dynamic. They move around a lot. They're very variable. So there could be some interesting implications here.
Are those density stripes real? Do you have high?
Yes, they are. I don't have a slide on it. Basically, the flows coming in are superalphanic and supersonic, and there is a series of shocks which occur. First an alphanic shock and then a sonic shock, and they effectively mean that by the time the plasma reaches the inner reconnection layer, it just looks like your standard Sweet-Parker thermal pressure versus magnetic pressure. But on the outside here, the kinetic pressure actually dominates, and so the system adjusts itself through these shocks, and there's magnetic flux pileup and all these good things that we can talk about another time, because I don't have the slides here right now, but they're on the computer.
And the inflow speeds are high because of the exploding wires?
Yes, exactly. So there seems to be a mechanism by which the plasma flows always end up as superalphanic coming off the wires here. And so you always get magnetic flux pileup in these experiments because you have more flux coming in, the reconnection layer can dissipate. And so the flux begins to build up outside. When the layer collapses, that actually changes because the Lundquist number drops so rapidly, the reconnection rate goes up and all that flux pileup goes away. So we start with a system with flux pileup and superalphanic flows, and later on it transitions to no flux pileup and subalphanic flows.
So if you count for the atomic emission,
Yeah.
How does that change the PRAD?
Oh, I'm so glad you asked. So what we do is we then post-process these simulations with an atomic code written by 2 collaborators at Imperial College. And this actually knows about all the atomic physics. So these are spectra as a function of time. So the darker colors are earlier in time when the layer is hotter, and the lighter colors are later in time when the layer is collapsed. And there are these lines here, which are the aluminum K-shell transitions at around 1.6 keV. They're very prominent early on, and then they disappear later on. And what we do with this post-processing is we make predictive images for the cameras which sit above. So the experiment is some tiny pixel down here, and these cameras sit a long way away. And we did predictions for what these cameras would see. And you can see that early on in time, you have all these little blobby bits. It's not very well resolved because it's pinhole imaging, it's a little blurry. Later on in time, 37 nanoseconds later, there only seems to be one plasmoid left, then it's darkness after that. So this was our prediction. Now, I have to say on the first shot, these cameras didn't function as intended, and so they were all dark. So we're hoping the next shots, which are in December, will get slightly better data. But the idea is that we should be able to actually resolve some structure along the reconnection layer, which would be very cool. And this was actually post-processed from a 3-dimensional MHD simulation, which I haven't shown you, where there is 3-dimensional structure of the plasmoids within the reconnection layer. So we see a much more complicated picture, but there is still enough collimation of the plasmoids in the outer plane direction that you get more brightly glowing regions and less brightly glowing regions. Pictures. So this is the array actually in the vacuum chamber. That's someone's knee behind it. Here are 150 wires on each of the wire arrays here. There's the CAD model on the side here, and this is a photograph. And also sticking in, we have loads of B-dot probes, those probes we had on MAGPIE in the experiments I showed you before. That's kind of what they look like a Q-tip, right? So sticking into the plasma. And then there were loads of cameras surrounding this. We had a spectrometer over here. We had diodes over here. We had a fast camera over there. We have lots of current probes. One of the things that impresses everyone who does pulse power about these experiments is we're able to measure the current, and that seems completely trivial to theorists, so I'm sorry, you won't be impressed, but it turns out to be incredibly hard to measure the current. We did it, so we were really pleased with that. And of course, this took several weeks to build, and it took a team of 4 engineer technicians sitting inside the center of a gigantic vacuum chamber about 5 hours to install, and within a microsecond, it was destroyed. So there we go.
This is very much
like the
Zen exercise.
Yeah, yes, exactly. Yeah, you have to let go of
whatever.
attachment. Yes, exactly. Yeah, you don't have to. So there we go. It's all blown up. All the wires are gone. Lots of things are shattered. But we got some data. So I'm only going to show you a little bit of data from this because we're still processing a lot of it, and there was an awful lot. But some of them are particularly amenable to being discussed. So we had surrounding the wire arrays in lots of different directions these little inductive E-dot probes that can measure the magnetic field. Here's some photos of them, and here's they are set up. We had like a 3D printed wire target so that we could get everything right without having a chance of touching the wires. So the wire arrays were installed later, and as Dimitri said, they take them out of their room downstairs that's about 100 yards away, and then slowly one person walks up one at a time with all these wire arrays, And then they get to the chamber, and the actual chamber is about 15 foot across and 15 foot deep. And the guy leans over and hands it down to a technician below, who then inverts it and installs it. And during this entire process, I was stood facing the wall because I could not bear to watch them do this. It was so nerve-wracking. If one of them had broken, that would have been it. There was no replacements. There was no way of
They're
fixing it.
very thin.
They're very thin wires, incredibly fragile.
So did they break?
A single wire on the inside was slightly kinked, and the technician managed to reach in for this tiny little gap with a pair of tweezers and gently put a little bit of pressure on it and straighten it out. But apart from that, it was perfect. Beautiful. They're very skilled. You know what they're doing there. So the nice thing about these probes is we stagger them at different distances from the wire arrays. And so that as the plasma flow comes in, it's dragging magnetic field with it. And we can look at sort of when the plasma arrives at these different probes and get estimates of the velocity. So this was the raw signal here, the voltage here, which you have to integrate up to get the magnetic field. The lighter colors are the probes which were closer in, and the darker colors are the probes which are further out. So you can see, as you'd expect, the plasma arrives at the closer probes first, and then it slowly arrives at the later ones. And so these are the magnetic field profiles that we got out here. The plasma is also radially diverging, so as it flows out, the magnetic field drops. So closer in, about 5 millimeters away, we got fields about 30 Tesla or so. And this is what the current pulse did. So we've got some time of flight from where the current was to where our magnetic field arrives on the probes. We can use that to do some crude estimates of how fast the plasma was going. It's about 150 kilometers per second. So these are pretty speedy. And we had one special probe here, the T probe, which was our star because we pointed a load of diagnostics at it. It was around the back of the reconnection layer, and it had a glass obstacle, a little cylindrical glass tube glued to the front of it. And you can see it. A closer zoom in that photo. And on that, we had one of these fast cameras like I showed you previously, but as opposed to looking for plasmoids, it was looking for this beautiful bow shock around the probe. And so the bow shock's very interesting because the opening angle gives you information about the Mach number. You've measured things like the magnetic field and the velocity already. So you can estimate all sorts of other plasma quantities just by looking at this bow shock. So again, this is very qualitative overview. I'm not going to show you any numbers at the moment, but we did get this quite nice image. But of course, it's a reconnection experiment. So what can we say about the reconnection layer? Not so much, because not all the diagnostics worked as intended. But the one thing that we do have is a time-integrated X-ray spectra. And so this is all the emission from all the time inside the reconnection layer. And this doesn't look particularly impressive unless apparently you're an X-ray spectroscopist, in which case this is great. I wasn't very impressed, but I'm told this is really nice data. And what we have is these lines at about 1.6 keV, which correspond to the aluminum K-shell. And that means that our plasma was likely about 100 electron volts or more, which is about 10 times hotter than the inflows. So the inflows have been heated up by a factor of 10. So there is some significant heating mechanism in the reconnection layer, and you might assume that that is reconnection itself, ohmic heating, things like that. And the only other bit of data we have is a diode, so a little X-ray diode that was just looking at the amount of light coming out of the layer. This is what the current pulse is doing. It rises and it falls down again, and this is what our diode does. We got a little blip of light in the center here, which we think corresponds to the reconnection layer forming, getting hotter and hotter, and then becoming so dense that it radiatively collapses. And this roughly matches what we had simulated with our MHD code. Apart from, we also expected another diode to light up here, and that diode didn't show any data. So either the diode was broken or our simulations were predicting something incorrectly. So this is why we do another experiment. We got another 2 shots at the beginning of December, just down the road from here, right? In New Mexico, it's not that far.
Yeah. When you go to New Mexico, is there a direct flight or the flight from Boston?
No, it's very tedious. It's always via Dallas. There's probably other places to go. But
Is there?
Sorry?
Can you go through Denver?
I probably could go to Denver. Yeah, maybe I should go to Denver and do a road trip sometime.
Beautiful drive.
Sure. So yeah, but so far just flying directly there. So. Okay, that's good. I just want to talk briefly about some turbulence stuff because it is something that going forwards I'm very interested in. Magnetized turbulence is very interesting because it has some of the features we've seen already from reconnection. It's got sort of flux tubes and current sheets, but as opposed to just a few of them, it's got this whole sea of flux tubes and current sheets between them. So I took this from a simulation paper from a few years ago. And there's lots of things that people want to predict and know about turbulence, but it's very hard to confirm as experiments. Things like anisotropy of the turbulence, if you have some guide field or mean field, the power spectra of velocity and density and magnetic fluctuations, and also this idea of intermittency, which effectively means the formation of coherent structures like these emerging flux tubes here. So how do we do this as an experiment? Well, we thought about a setup where we could just smash 8 flux tubes together. So we start with a wire array, which instead of exploding is imploding. So the J cross B force points inwards. You've got 8 wires like this. And around each wire initially, as the current starts flowing, there's an O point because there's current flowing through a wire. But as the current rises, those O points begin to detach and they push inwards, and you effectively have 8 flux tubes merging towards the center. This comes from some old simulations that are actually done for a different purpose, but the idea is exactly the same. You can see my glowing CAD model there. You get these sort of teardrop shapes of plasma, and the leading edge here has an O point of magnetic field inside it. So we did these on MAGPIE. This is looking from above with that fast camera we talked about before, looking at the light being emitted by the plasma. And you can see in this first frame here, these teardrop shapes are forming. And if I play the movie, you can see early on in time when it restarts, there we go. The teardrop shapes collide, and they create this column of plasma at the center, which seems to last for an extremely long time. But of course, with the resolution of this camera and the signal's noise, you can't say anything about this plasma. It's a bit messy. I'll show you some data in a moment that shows that, in fact, there seems to be a lot of turbulence inside here.
Do you have a picture of the magnetic field here?
No.
Can you describe the configuration?
So the magnetic configuration is going to be,
this
to
is-
start off initially like this. Then, of course, once these collide, whatever the turbulence or whatever the reconnection between these and how they interact is going to create something more complicated. So effectively stirring this system at a length scale of about 5 millimeters here, and then that's sort of the outer scale of the turbulence. And then,
is there no out of plane?
in this experiment, there's no outer plane, so this is like 0 mean field, 0 guide field kind of experiment. We could think about adding it in a future experiment, but at the moment there's nothing.
But also here in, as I understand, so the setup is, purposefully or not, is very much axially symmetric.
Yes.
So whatever you create is,
Well,
until it goes unstable.
until it goes unstable. So we
Right,
can have a look at that as
basically,
well. Yeah.
When you get started, it's all two-dimensional.
Yes. Yeah. So initially this is like a slice, but this is a slice through the top, the middle, and the bottom. It should all be the same. So we have some estimates of the plasma parameters from other experiments and from this experiment. This was a work I started during my postdoc and never finished. So we don't have a full story here, but some ideas of the dimensionless parameters here. This is still a very collisional system. So this is very MHD. Our mean free path is much less than our outer length scale here. The betas are roughly 1, as we've seen with most pulse power experiments. That's true. We think we have high Reynolds number and high-ish magnetic Reynolds number. And in these experiments, our Prandtl number is less than 1. So this is the sort of turbulence we think we can study with this. And these are very approximate signs because we haven't measured all these properties, and also we can adjust the properties of this system by changing the geometry of the wire array, its diameter, and things like that. So I said that the image that we saw in the middle here wasn't very convincing because you just saw like this blob, but we can also do laser interferometry on this. So this is a large-scale laser interferogram. You can see the fringes which have been bent. These are flows of plasma coming in from each of the wires here. And then in the center, things get messy. So if I blow it up, this screen isn't doing it justice, but there are lots and lots of detail inside all of these, inside this column here. And in particular, there's little regions in which we can see interference fringes and regions where we don't see any interference fringes. And this suggests there are regions of higher and lower density where the laser beam can propagate through and where it can't. So again, this is not a measurement of turbulence. This is just saying there is structure, and this structure is much smaller than the outer scale that we stirred the system with. And we can also have a look at it from the side. So here we're looking actually from the side view of this thing. There's 8 wires. There's 4 black lines here because the other 4 wires are shadowed by them. The plasma flow comes in from the left and the right. And here is the column of plasma in the center. And you can see there's a huge amount of structure inside this as well. It is no longer axially uniform. Now, when you use wire arrays, you always have some axial modulation on the plasma flows coming in. That's what you see here. So we are driving this system with some wave number in this direction, but it's pretty uniform. And when you stare at this shadowgram for a little bit longer, you see there's much smaller scale. So again, we seem to have transitioned from this larger scale stirring to smaller scale stirring and stuff. So this is an interesting experiment. This is basically all the data I have. One of the things, again, with this experiment is that the plasma just doesn't hang around for long enough. right? By the time we've developed something nice like this plasma, the current pulse turns off and it dissipates. So if we could drive the system for much longer in a sort of quasi-steady state, that would give us much more time to look at how the turbulence evolves and things like that.
Could you go back to the slide with the scale tables? Did you have kinetic scale? No. What are the kinetic scales here roughly?
What quantity would you calculate to get that?
Skin depth.
Oh, so actually skin depth is probably about 1 millimeter. So it's smaller than the stirring scale, but on the order of. Yeah. And the Larmor radius.
The entry path is the shortest.
Is the shortest length scale in this system.
So smaller than the skin depth.
Yeah. So it's unlike some astrophysical or space plasma that people study. Yeah. And the Larmor radius, I don't know off the top of my head. I think it's probably on a similar scale.
Yeah.
The trouble is the collisionality is so high that the ions are almost certainly not magnetized, but the electrons may be magnetized in the terms of the Hall parameter. So, yeah. So all that leads me to PUFFIN, which is the new machine that we're building at MIT. It has all the features that I showed you at the beginning of the pulse power. So we've got some capacitors, which is where we store all the energy. These get charged to 70 kilovolts each. We store about 40 kilojoules of energy. And then that power is transmitted down these transmission lines, as well on the left and the right. You can see it in this cutaway better. They're coaxial transmission lines. All the energy flows in the gap between the inner and outer conductor. And then there's some complicated T-junction here, but effectively the energy gets into this tapering transmission line that gets focused into the load region. So the load, things like those exploding or imploding wire arrays, would sit roughly here. And then we have this nice vacuum chamber with lots of windows so that we can have a look at whatever plasma we've made. So most of this is now actually designed. We're very, very close to actually placing the order for all the metal and start to make it. And what's my next slide? Oh, okay. This is probably less interesting, but we're going to get about 600 kiloamperes with a 1.5 microsecond rise time from our circuit modeling. This is less than other machines I've worked with. So MAGPIE was 1.4 megaamperes, so more than twice as much. But the rise time is much slower. And so on MAGPIE, it was only 250 nanoseconds. Here, we have this region where the current is almost constant for almost a microsecond. It changes by less than 10%. So we have this sort of plateau region where we can drive our system in sort of quasi-steady state. And just to give you some timescales, the Alphane timescale in these systems is usually about 50 nanoseconds or less. And so this is many, many, many Alphane timescales. So the system really has time to settle down into some sort of steady state, which is very different from other pulse power machines. Pictures. Here's the big crate arriving from France with all the pulse power on the crane. Here's me sitting proudly on my new acquisition. So that's how tall they are. They're about 8 feet tall. And then this is the platform that they've been building in the West cell here. So there's lots of support structure to hold everything up inside it. So what sort of things are we going to look at? Just going back to this, I've already talked a lot about reconnection and turbulence, but I'll just highlight some things to do with shocks and jets and instabilities that might be interesting. And of course, we also need to do loads of diagnostic development because measuring turbulence is an outstanding problem that we don't know how to do at the moment. My grad student, Richard, has done a lot of work looking at bow shocks. On MAGPIE was old data, and we want to redo these experiments on PUFFIN with a longer time scale. Effectively, he sticks one of these VDOT probes in, and he looks at the shape of the bow shock. Like I mentioned on Z, that shape of the bow shock gives us lots of information. So we're trying out our ways of getting data using MAGPIE data, and then we're going to apply that to Z as well. And this is something we can do on PUFFIN because we're interested in how the shape of this shock changes in time, whether it's actually stable or whether it oscillates. There's also been a lot of interest in jets. These jets have been made in various pulse power machines for a while using a different load configuration. Some people are interested in studying these jets because they may be relevant to young stellar objects, astrophysical systems which have jets or black holes. Other people are interested in jets because it's a nice collimated beam of plasma. And so in this experiment on MAGPIE that I helped with, we placed an obstacle here. This is an acupuncture needle. It's about 100 microns across. And we directed a jet of plasma directly at it. And what surprised us is not only that we got one shock at the front, but we got a series of nested bow shocks all the way back here. And these bow shocks are also extremely unstable. So this is interferometric imaging, and this is Schlieren, which shows up density gradients very strongly. So this is not understood. This work wasn't really continued, but it's something that I'd like to try and PUFFIN because how fast these shocks move and how unstable they become is a really interesting question. And you want to be able to disentangle that dynamic motion from the dynamics of your current pulse. So if your current pulse is changing a lot, you're changing the inflow. And so, of course, you're going to change what happens here. If your current pulse is constant, then you've at least removed one variable, and you can see what the actual dynamics of this system is.
And what do you mean by jet here? Is there a magnetic field?
So the jet is, so the jet is sort of a collimated jet of plasma with current flowing through it with helical magnetic fields around it that seem to be confining it. So there's been a lot of work on these jet systems on pulse power over the last 15 years or so, where they've tried to understand what role the magnetic fields have in this. And so again, the jets are sort of surprisingly stable, given that they should be MHD unstable, and that's something we don't really understand either. But also when we observe astrophysical jets, they appear to be surprisingly stable as well. So there's some sort of questions which are similar. We did some fundamental research on some instabilities. We did some experiments at Cobra in Cornell last year, again with Richard. Here we were looking at the magnetic radiator instability. So effectively,
What is Cobra?
Cobra is a pulse power machine at Cornell, the Cornell Beam Research Accelerator. None of the acronyms really make sense, but you've got to have a cool animal.
Or MAGPIE and PUFFIN?
MAGPIE is the mega-ampere generator for plasma implosion experiments, and PUFFIN is the pulse of fundamental investigations. So, yeah, you know what you can. I think people normally start with the name and then work backwards, right?
But these are names of birds, right?
Then birds, there's also Maze out of Michigan. It's a very Midwestern name. That's the mega-ampere inductive Z-pinch experiment. And there's Cesar in UCSD, and I don't know what that stands for. So, people have a lot of fun. So in this experiment, we effectively had a plasma being generated here in some thin wires and a very strong 100 Tesla magnetic field that was pushing the wires away. And so this is a form of the Rayleigh-Taylor instability, where instead of having gravity as your accelerating force, you have magnetic field. And we were looking at the stability of this interface here. And in these images that we got at various different times, you can see the formation of little spiky things that are reminiscent of the MRT instability. So this was very preliminary work that we did just in a short experimental campaign to prove that the system worked. And we want to continue this as well. And as I keep saying, if you go to a longer pulse length, you have much more time for these instabilities to grow. You can maybe look at the non-linear growth of these filaments and spikes as they start to merge. So this is another thing that PUFFIN would be ideally suited for.
Yeah, it almost looks Kelvin-Helmholtz-ish in
Yes.
that swirl there.
Exactly. So there's a very interesting effect that people well spotted, by the way, because that's really tiny. There's a very interesting simulation papers from the late 90s where they look at two fluid effects. And the idea here is that the electrons are flowing differently from the ions, and they actually create the shear flow that allows the MRT to go Kelvin-Helmholtz unstable. So it's like a simultaneous shearing and acceleration in that direction. And they see qualitatively these sorts of shapes showing up here. And we know that the ion skin depth here is on the right sort of scale for those effects to be important. The difficulty is actually simulating that, because there are very few codes that can handle these sorts of experiments and two fluid effects. So Perseus might be one of them at Sandia. So we really want to simulate this, but our standard code, Gorgon, at the moment, there's a grad student working on two fluid effects, but it's not there yet. So yeah, we basically need to do these experiments again sometime and get some really nice data and then compare it with simulations. And there is some theory for what the growth rate should be with two fluid effects. So there's some other stuff you can compare. Okay, final slide. So I've talked about a lot of things. Thank you for your patience and for staying a little bit longer. So we talked a lot about magnetic reconnection on MAGPIE and the plasmoids that we saw there. And we have very nice diagnostics there to look at all the different energy components. I talked about scaling that up to Z, very high currents where we have strong radiative cooling. Initial on Z is the diagnostic suite is not well suited for the experiments we're doing. And so we've had to adapt a lot of things. And sometimes we just didn't get any data. So we've got more shots and hopefully we'll improve on that. One of the big things I want to go after is magnetized turbulence. I think this platform is very exciting and very simple, but already seems to generate an awful lot of interesting stuff. I'd love to do Thomson scattering through this and look at how the velocity and temperature varies along a chord. And I'd like to do Faraday rotation imaging as well to look at what the magnetic field is doing. And all of those things I intend to do on PUFFIN, which is the machine that we're building at MIT that should be doing first plasma next year. And the overall goal, again, thank you, Dimitri, for providing this inspiration. There are lots of these interesting processes. So how many of these processes can we actually study in the laboratory? So thank you very much.
Thank you. I'm going to stop recording.